Uh, Good evening, everyone. My name is Harini. I'm a PhD student in Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. I'm doing NPTEL TA-ship for the course Watershed Hydrology under Professor Rajendra Prasad sir from IIT Kharagpur. And in today's topic, we will be discussing about what are the different types of hydrological models that are available and why hydrological modeling is important. And also, we will be talking about how machine learning can be used in hydrological modeling, etc. Okay, so let's start the lecture. So initially, I will be giving introduction for all these topics, and then we will discuss some MCQs related to this topic. Okay. So first, let's start with what is model. Okay. What is model is the it is a simplified version of the real world. Okay, with a little bit with few assumptions. So model. So model is a simplified representation of reality with some assumptions or essential features. So why modeling is important? It is important to save the time and money. Okay, so every time we cannot go and get the data. If suppose we are trying to simulate, we want to know how the stream flow is at a station, and when we want to know when it can flood the what amount of stream flow can flood that area. Then what we can do is we can set up a model for that area, and then using rainfall or any other input data, we can simulate stream flow using these models. And based on some trial and errors, we will know like how much amount of stream flow can flood this area. So these things, and also it will take less time, okay, than waiting for the flood to actually occur, uh, which will damage the society as well, right? So that's why. So it is important to develop these models to save time and money, also to understand the real environment through representative models, and to avoid the risks. Suppose if we wait till this occurs, then what is the use? We will be losing damage and also property loss, life loss, etc. So all this can be avoided if we know that this amount of stream flow can result in flooding, then we will take precautions ahead. So this kind of risk can be avoided. So to avoid risk associated with tempering the real thing. So we also know how land use, we can also create scenarios like how land use can affect the stream flow. Suppose like if the area before is covered with forest, how the stream flow, how the runoff, how much amount of runoff is generated. But once the land use is changed to like urban areas or some other kind of thing, then we will know how much runoff will occur, and we will know the risk associated because of this kind of land use changes. Okay, so that's how you can tamper the real things as well in a model, and to communicate with others. So how this is helpful to communicate with the others? So if we have uh, suppose we have a model which shows us how much amount of stream flow can occur because of this. So by visualizing it, creating like graphs or time series, all these plots, we can show the people and we can communicate with the people that if a place receives 100 of rainfall, this is the runoff that can occur, and this much amount of flooding can area can get flooded. Like that, we can give data, visualize data also. So that's how these models are important. So mainly there are three types of models. Okay. So first one is physical model, in which we will be applying like physical equations uh, to relate the input and output. Suppose in case of hydrology, we have like mass conservation, momentum conservation equations, right? So all this will be included when you are developing a model. So when we want to know how much amount of how this rainfall is converted to runoff, we will use all these kind of physical equations like mass conservation, momentum conservation, etc. to develop a model. And another one is analog model, and the next one is mathematical model. So mainly we will be concentrating on a mathematical model where we will have some parameters and variables which are related each other with some mathematical equations. Okay. And in this, some physical process also will be involved. Suppose we have Q equal to CIA is the rational method. Here, if we know uh, rainfall intensity, we can generate the stream flow. Okay, this is a mathematical equations linking the rainfall intensity to stream flow, right? So this is one kind of model. So when we talk about models, we will generally have confusion between what is modeling system and what is a model. Okay. Suppose all these models, like whatever we are trying to set up, suppose we are trying to generate from rainfall, we are trying to generate this runoff. What we will do, we will create some equation or we will use some softwares to develop it. So the software that we are using is called a modeling system, in which only equations are there that simulate hydrological processes. Okay, this is modeling system. And in case of model, what we will do is software plus the data. So that, suppose Q equal to CI is our modeling system. Then if we have this data, okay, rainfall intensity, area, and C value, coefficient value, runoff coefficient value, then the software or the equations plus the input data, together we call it as model. Okay. So it is modeling program plus data specific to a watershed. Suppose you might have heard about hydrological models like SWAT. Okay. So SWAT is a software. Okay. But if we give input into the SWAT like rainfall, evapotranspiration, soil moisture, etc., whatever the inputs that the model is required, and the also output, then the software plus data. With these data sets, it is called as model. Okay. Then we will be talking about mathematical. Yeah, let me write in the next one. So mathematical modeling processes. So how do we model these processes mathematically? Suppose we have real system. What we will do from that, we will formulate a model. Okay. And then from the model, we will draw some deductions or inferences, which is called as model conclusions. Okay. And from that, what we will try to do is like, since real and the model conclusions won't be same, we will try to interpret so that we can get real conclusions. So our main aim is that suppose we have a real time problem we need to get some kind of conclusions, or like some we need to know what kind of methods to apply. Suppose we know that this, suppose a part of Bangalore city or Chennai or any other city is getting flooded, so we need to know how much area is getting flooded, where these flooding areas are concentrated. So that that conclusions are called real conclusions. And what we will do is that to get those, first we will set up a model for it using some hydrological model. And from hydrological model, we will, by giving inputs and based on the outputs that we are getting, we will get some model conclusions. But since these models are not exactly real-time replica of a real world, what we have to do is we have to correctly interpret these conclusions to understand the real system. So directly from real system, if we can draw real-time conclusions, then it is a direct approach. All these are indirect approach. This method we are following is an indirect approach. So similar to that, we have an alternative representation as well. Suppose we have real world and we have input parameters which we can obtain from real world, and we'll set up a model. From that, what we will try to is do is we will formulate a mathematical equations, and based on those equations, we'll try to solve the equations and get some generate some output or get some results which are model results. And using that, we will get model conclusions. And then what we will try to do is we'll try to interpret and or validate the results with real time. Suppose if we have stream flow data. Okay, so stream flow observed data we have from stay right. Okay, at some from Gorges, then what we can do is from real world data we can get rainfall, evapotranspiration, and stream flow data, and we will try to set up a model, formulate the model using mathematical equations, and once we solve those equations, we can get simulate stream flow. And this stream flow, what we can do is we can validate it, like test it, whether it is matching with actual real time observed stream flow. Okay. And then what we can do is, suppose if it is matching and it is performing but good, then we can set up this model to generate for different scenarios. Like I have said, like if suppose there is a land cover change, then how the stream flow is changing. And suppose if which how much amount of stream flow can cause flooding. All these deductions we can make from this model. Okay, first let's see. We have used terms like formulation, deductions, interpretation, right? Let's see what does this mean. So first, formulation is just nothing but the hydrological processes. We will try to develop them using the mathematical equations. Hydrological processes are studied from mathematical equations. So in this, mainly we have to decide what aspects of. So in this, mainly we have to decide what aspects of real system should be incorporated. Like suppose we in a real world we know like different types of hydrological process occur within a watershed. Suppose we have interception, infiltration, runoff, and then percolation, base flow, etc. So when you are trying to model all these things, it will become more complex model. Okay. So what we try to do is we will make some assumptions. Like suppose we assume that there is no interception loss in this place. So like that, we have to decide few things on our own. Okay. When you are trying to formulate a model. And also we need to know what kind of model you want to use, whether we will be discussing these things later, what kind of model is, like whether it should be a lumped model or distributed model. So lumped model is like for entire basin we will average the data and we'll get only one single value as outputs. Okay. So in the case of distributed data, we will get the output value at each location. Suppose we are trying to in a basin we have grids. Okay. And we have rainfall temperature data at each grid, and we'll try to simulate stream flow at each grid. But in case of lump model, for this entire watershed, we'll have a single stream flow value, and we also give input a single rainfall and temperature values. Okay, because we'll average it for this entire basin. So it depends what kind of model you want. Whether you want to understand how this hydrological process are varying, especially, then you will go for a distributed one model. Then we have to also make some kind of assumption. Suppose I have discussed earlier, if we are assuming that there is no interception loss, then that's one of the assumption, and you have to mention that when you are formulating a model. So then next one is deduction. So deduction is nothing but solving the equations by running a computer program. So like this, like I have told you, suppose we have rainfall and temperature and we are trying to generate excess rainfall, and from that we are trying to generate base flow, also quick flow, and from these two we are generating a stream flow value. So all these things, what we have to do is there will be mathematical equation linking the variables. Okay, from rainfall and temperature, we will have a mathematical equation to generate excess rainfall. And from that, we will have one more equation to generate base flow, another equation to generate stream flow. Like that, we'll have multiple equations within a single hydrological model. So then what we have to do is like we have to solve these equations, then only we can simulate the stream flow, right? So this solving we have nowadays we can do with by computer because that's easier. So the solving equation by computer programming is deduction, and then we have interpretation. So as I have told, interpretation is nothing but we have to convert the model conclusions to real-time conclusions. Because we, like I have told in the hydrological models, we will make assumptions to simplify the model. Okay. So that's why model conclusions to be translated into real-world conclusions. Okay. So this is the alternate figure that represents the mathematical modeling procedure. Then let's look into few of the principles of modeling. So when you are trying to set up a model, you have to remember that the model should not be complicated. Okay. So because if you are developing a very complicated model, it will take a lot of time to first set up the model, and also for calibrating and validating this kind of models, it will be very difficult. So it is always better to go with a simplified version of the model. Okay. So do not build a complicated model, and so beware of modeling the problem to fit a technique. Suppose we are very good at one method, okay, we can we are good at using this q equal to rational method to generate stream flow. So suppose, but we are this also has some kind of limitations, right? So we have to be careful whether you can use that equation in the case of the purpose that you want to do. Okay. And then model should be validated prior to implementation. So validation means like you have to check the modeled results with the observed results. So if they are not matching, or if they are not very accurate, the modeled results, then it is no use to apply this model for our main objective. So first we have to check whether it is performing well. It's able to simulate the data accurately with the observed data. Then only we have to implement for our objective. So also model should not be taken too literally. That means we should not assume that model will accurately exactly predict whatever the observed data is. Okay. So because we are making a lot of assumptions, there will be some kind of error associated with it. And also we have to be beware of overselling a problem model. So if we know that there is a limitation with the model, we have to be very particular in mentioning it. So we should not be doing that, be saying that it can do everything. Okay. So that's why we have to be beware of overselling it. And also model cannot be any better than information that goes into. Suppose if we have a wrong data, or suppose we have while recording the rainfall data, we have made an error. So the error will be getting translated to the output also within the model. So when you give correct data, then only you should expect that the results will be also accurate. Okay, and also the next principle is model aid decision makers in making better decisions. So it cannot make a decision, but it will help the decision makers in making a decision. So the next one is modeling protocol. Let's look into the steps. First one is we have to define purpose. Purpose is like whether we want to simulate extreme stream flow data, or we are trying to look into how the stream flow is occurring at some location where we don't have any data. We are trying to set up a model for that kind of purpose. We should define first the purpose, and then we have to develop a conceptual model. Okay, from in this the field data will be going as input. Okay, then we have to do code selection. So different types of codes are available, like based on suppose if you are working on Python itself, when you are trying to set up a mm, conceptual model, you'll have different ways of setting up that model. So you have to select what kind of code is good for your model. Then if the code is suitable, if it is suitable, then you have to proceed further. If it is not suitable, then you have to develop a code. Okay. And once the code is fixed, okay, then what you have to do is model construction. Then you have to check the performance of the model, whether it's able to simulate the stream flow or like the output that we want accurately. Use and also we have to do calibration and validation, which we will be discussing later in the coming steps. And then we will simulate the output. So this simulated data, we have to represent it, visually represent. Suppose we are trying to simulate stream flow, then what we can do is we can plot a time series of how the stream flow, the sim modeled one and the observed data is. Okay, then we will get an idea whether the model is able to capture the observed data properly or not, like that. So all these steps are involved in when you are trying to model it. So first we have to know what is the objective. Then we have to decide what kind of model, whether conceptual model, physical model, what kind of model you are trying want to set up. And in that you'll have some inputs which we can get from field. Okay. Then we have to select the code. Suppose there is a code already existing. Suppose we are using models like SWAT. There is already code written for it. It's a well-developed model. So you will just use that model. We will construct the model, like give the our inputs, like for our region, and then check whether it's able to simulate the stream flow property or properly or not using performance criteria. And we'll validate and calibrate the model, okay, to get the parameters of the model. Then we will, after the calibration is done, then using those calibrated parameters, we'll simulate the stream flow. And the simulated stream flow will be represented like graphically or any other method like your wish. So if there is no software, you are trying to develop your own model, then you have to set up a model. Okay, code development step will be added, and then similar steps as the already existing code you have to follow. So then what are the advantages? So what are the advantages of a model? First is it will help us in understanding complex system. It's also helpful in prediction and forecasting. Suppose we have now we if we have IMD data is giving us rainfall forecast. Using that we can forecast stream flow as well. Then we will know when flood can occur or drought can occur. All this we will know ahead. Okay, and it is cost effective analysis, like I have told, based on different scenarios, how the stream flow changes, all this. Okay, we can use a model directly and get the data. So that is cost effective. We don't have to go there and do some practical things, right? And it's also used for risk assessment, like in case of droughts and floods. So then, and also it's a communication tool. So also let's talk about what are the disadvantages associated with it. First is we need a lot of data. Okay, because if you want to calibrate and validate the results, you need a huge length of data. Then only we can set up a proper model. Next one is calibration challenges. It's very difficult to calibrate the complex model, and sometimes we might not be able to calibrate the model properly because there is the data is not proper, and you have to deal with uncertainty. So the model can also be overfitting, and there are the models are simplified versions of real time, and also it has lot of reason we they have lot of assumptions as well. Okay, so these are the disadvantages of the model. Now let's look into few of the questions related to this topic. So the first one is what is the primary purpose of hydrological modeling? So option A, yes. So, so now let's look into some questions. So dash is a simplified representation of something real but with essential features. Option A, modeling. Option B, model. Option C, modeling system. Option D, modeling protocol. So as we have discussed, a model is a simplified version of the reality. Okay. Then what are the three of the most important things to consider when constructing a model? First, calibration, testing or model range. Second one is cost, time availability, skills. Option C, resolution, parameterization, testing. Option D, purpose, resolution, resources. So when you are constructing a model, you should be sure about the purpose. For which purpose you are trying to set up the model. Based on that, the model will also change. So purpose, and at what resolution you want the model to perform. Suppose if you want in monthly scale or daily scale, or if you want, I have told you, if you want the data at each point in a grid of a basin, then you have to go for distributed water. Or if you want a single value for a entire basin, then you have to go for lump model. So that's all. Resolution is also important. And the resources, what kind of data is available, and we also need to know how how resource management can be done in the watershed. These are the main important things that we should consider when you are constructing a model. So next question is, dash is a process of the mathematical model in hydrology that involves analyzing the results and drawing meaningful conclusions about the behavior of hydrological system. So option A, deduction. Option B, formulation. Option C, interpretation. Option D, optimization. As we know, formulation is like setting up the model. Then deduction is like you are trying to solve the mathematical equations in and get the results in the model. Interpretation is like once you have the conclusions of the model, you are trying to draw a real life conclusions from it. So the answer will be option C. The next question is, modeling protocol involves option A, code development, option B, model construction, option C, performance criteria, option D, all of the above. So if you have seen this, I just discussed about the steps involved in modeling protocol. You can see that we have to develop a model and then sorry, we have to develop a code and then construct a model. Then we will use some performance criteria methods to evaluate these models. Okay. So all these three are included. So the option is the above. The pro. So now let's look into the hydrological models. So how hydrological models can be applied? What are the applications involved in hydrological model? So when we are trying to set up hydrological model is for to help us for planning, design, and operation of projects, and also to conserve soil and water resources and to protect the quality. Okay, so first it is used for planning, design, and operation of the project, and also it's employed in various applications from management to engineering design in watershed. Okay, then also we have to know answer the Penman's equation. Okay, what is Penman's equation is trying to tell us? It's like what happens to the rain. So we need to know what is happening to the rain that is coming into the watershed, whether most of it is getting infiltrated or most of it is converting into runoff. So all these things we can answer only using a hydrological model. Then what is the need of hydrological modeling? So once you set up a hydrological model, we can study various processes. Suppose, as I've told you, we have a model. Rainfall and temperature are the inputs. We generate excess rainfall. Also, we can generate base flow, quick flow, and then using that stream flow. So all these variables are generated using two input variables. Okay. So we'll get an idea of how these variables are varying across basin or within basin, how they are varying with season. So that We can know when we will have less amount of stream flow for water management, and if we are going to face floods in near future, then we can apply some mitigation measure. So all these like various processes can be studied simultaneously within a hydrological model. And also it's an integrated system. As you can see, we are integrating different types of processes together and then we are trying to study it. So it's an integrated system approach. And also using this, we'll get an idea of hydrological parameters, which are very difficult and impossible to measure. So suppose if in some cases, what the hydrological model can also give is the like porosity, hydraulic conductivity of soil, groundwater. So all this also few of the hydrological models can generate. But in the real case, we don't have that many instruments to measure how much of groundwater is available at each location. So, using these models, we will get an idea of how the groundwater is fluctuating within an area, how hydraulic conductivity is fluctuating. All this, we will get an idea. Okay. And then, as we discussed, we can also forecast flood peaks and runoff values using the hydrological models. The next one is we will be discussing about mathematical hydrological models. So in this mainly we have two parts. First one is hydrological core, in which scientific basis for process description, and we will have a technological shell like programming, user interface, and pre and post processing facilities. So as I have told you, suppose if there is a hydrological model like this, then what we will have some mathematical relations between each variable. Okay. So suppose rainfall temperature, we are trying to simulate excess rainfall. There is some mathematical model. Okay, all these mathematical equations are developed based on some scientific basis. Okay. And then these equations can be only solved using programming or interface. And suppose the data that you are having, okay, the rainfall, temperature, and excess rainfall, it has lot of missing data or something. There is some wrong with the data. Then we have to pre-process the data. Then only we can get good results. Okay, all this you can do in programming. So then let's look into different modeling approaches. So, case of mathematical models, we have three types of classes. First one is empirical, in which we will have relation between input and output. Output. There is no physical basis for this relationship. Okay. These are also called as black box. Okay. So we don't know how they are generating the output, but we will have some input and output, and there is a relationship between the input and output. This next one is process based. So based on fundamental physics laws, we will develop some equations to Describe these hydrological processes based on fundamental physics and process governing equations. Process based models are developed. Next is conceptual. So in this, we will have some processes which are explained based on the physics behind it. Some are just in relationship between input and output without any physical meaning. Okay, so only some processes are explained. Then based on nature of the models, there are two types. First one is deterministic. So deterministic means a single set of inputs generates a single set of output. So if we have rainfall value as 10 mm and temperature as 29 degrees Celsius, then these two together will can suppose if it is generating 5 mm as excess rainfall, then the in a deterministic model, always the result will be 5 mm if the rainfall value is 10 mm and temperature is 29 degrees Celsius. So that kind of models are called as deterministic model. Then we have stochastic or probabilistic. Stochastic or probabilistic models in which some input parameters and processes follow stochastic nature, or then it's also called as statistical distributions. So in this case, what they do is suppose we have similarly rainfall equal to 10 mm, temperature equal to 29 degrees Celsius. They'll give multiple outputs as excess rainfall. They'll say suppose 5 mm can occur with a probability of 60%. With 60% chance, the excess rainfall can be 5 mm. And with 10% chance, it can be 3 mm. With 20% chance, it can be 2 mm. So like that, with some probability, they will assume the excess rainfall value. So this kind of approach is called as stochastic or probabilistic approach. Then based on time scale, we have first one, steady state. Steady state means the variables are unchanging with time. Okay, so they suppose we have land use land cover. Okay, it doesn't change much with day in a daily time scale, right? So if there is a forest area, tomorrow also there will be forest area. It will take some years for the land cover to change. So these kind of variables are called the steady state. So the variables which are changing with time are called as steady state variables. Variables unchanging with time. Then we have event based. So if you remember, we have talked about event. Suppose there is a rainfall event that is occurring, then the hydrograph that is generated is also event. So for an event, we have talked about suppose like 10 mm of rainfall occurred in first 6 hours, then 2 mm of rainfall occurred in next 6 hours, like that. So that's an event. Okay, for that we are trying to set up, we are trying to find out how the hydrograph looks like. So this is a event based approach. Then next one is, next one is continuous, in which variables change and are dependent on previous state. Okay, at each time step, the variables are changing. Suppose today we have huge amount of rainfall. The stream flow will be very huge. And tomorrow there is very, today some 100 mm rainfall has occurred, which has resulted in 50 mm of excess rainfall. Okay. And next day there is a rainfall of 20 mm. Still it is giving some 15 mm of excess rainfall. This is because of today's rainfall, the soil is completely saturated. So most of the rainfall that is occurring tomorrow will be converted into excess rainfall. So like that, it is dependent on previous state and also it is changing with respect to time. So that those kind of variables are called as continuous. Then based on time step, we have different types of models. So time step means like, are we trying to look at the data in monthly scale, daily scale, or minute? So generally, if we are developing a hydrograph, then we are concentrating at hourly scale, right? So every minute is important. If you are looking for a how the stream flow is fluctuating with a basin or watershed, then we go for monthly or daily scale. So it depends on at what time step you want to set up the hydrological model. Then based on different spatial scale, there are different types of models. Like we have multi-basin model, single basin model, sub-region model. Then based on the spatial details. Sorry. Okay. Let's continue with next spatial details. As we have discussed, there are two types. First is lump model. Next one is distributed model. Okay. So we will have lump means, as I have told you, for entire basin we will average the input data and also we will get one single averaged output data. For distributed models, we will assume the input data will be grids and also the output data also will be coming in the grid format. So we will have at each grid we'll have input and output, so we can know how the data hydrological process is varying across the space. And also we have like models like 1D, 2D and 3D models. So 1D model, for example, channel flow is a 1D model. How the stream flow is fluctuating at a particular station is a 1D model. In case of 2D model, we are trying to simulate overland flow. Our overland flow means like how much of water is flowing on the land. So that will be 2D flow. And then 3D means we are trying to look into groundwater also. So that is kind of 3D model. So generally we will have mostly in case of lumped conceptual models. In case of distributed, physically based models are most common. Okay. So, and also if you see here, we are talking about if the models are empirical, lumped, or long time step, and if how these few features are varying once you go for conceptual or process-based model, where process-based model has distributed 3D and short time steps. Okay. So you can see the complexity is increasing. So if you have a simple lumped empirical model, then it is a very simplified model. So, but if you are trying to set up a process-based distributed model, and we are trying to look into like short time step, a daily time scale, okay, then it will the complexity of the model will increase, and also the increasing reliance on data to build will go from right to left. And you can see the increasing reliance on process understanding will build if you go for process based model in distributed case, because in distributed case we'll have an idea of the processes that are varying across space, and also we'll get more information from these kind of process based, and also we can trust this because these models are developed based on some physics behind. Then, as we go for process-based distributed models from lumped models, the amount of data required is also increasing. Okay, so here if you have in case of lumped model, one single time series of rainfall, temperature, but in case of process-based, at each grid point, we'll have a time series of temperature and precipitation. So the data is also increasing, data amount. And also computational requirements are increasing. The resolution will be very fine resolution results we will get from a process-based distributed model and compared to lump model. Also, we will have increasing reliability for scenarios and projections as we go from left to right. So next, look into different catchment models. So first, we will look into deterministic models. In that, we have empirical model. As we have talked, it's a just relation between input and output. So these are sometimes referred to as black box also. And the relationship can be established using some statistical method or data driven method. It depends on the developer. Then we will have conceptual model. The conceptual models are considered as gray box models. So here generally they are lumped, and parameters and variables are average over the catchment, as I've told before also. Since they are lump models, and physical sound structure, but the equations are used. So we know that from rainfall, some excess rainfall is generated, some amount is converted into that, some amount is going from excess rainfall, it is going for base, no quick fill, like that. We know we have a physical idea of how this process occur, but the relationship will be developed based on some equations which doesn't have any physical meaning in case of conceptual models. Then in these kind of models, calibration is very important step. Then we have physical based models, which are called as white box model. So as I told you, we will generate we will set up these kind of models using physical equations like mass conservation, momentum conservation, and energy conservation. So, and also these parameters that we are updating will have a direct physical significance. And mostly these kind of models are fully distributed models, and they are very huge and complex. They require huge data and also complex models. So then we have stochastic models. These are similar to empirical black box models. Suppose if you see in this deterministic model, you have a cause and you have an effect, and you are getting one single output. But in case of stochastic model, you have a cause and you are getting multiple outputs. with a probability distribution, right? So this is the main difference between deterministic and stochastic model. But mostly in stochastic model also the model that we are using is a black box. We use some statistical method to generate this kind of multiple outputs, and we don't have any physical meaning for how this why this statistical method is used. Okay, then we have joint stochastic deterministic model. One example for this is, suppose in this case what will happen is we have a deterministic core and stochastic methodology, which will take care of uncertainties in the parameter and the variable. Okay, so one example for this kind of model is Sacramento and NAM. Okay. So these are the different types of hydrological models that are available based on different characters like nature, time step, time scale, spatial scale, and mathematical models, all this. Okay. So now let's look into few of the problems related to this part. So what is the primary purpose of hydrological modeling? Option A, to control flood events. Option B, to simulate the movement of glaciers. Option C, to predict the precipitation patterns. Option D, to understand and manage water-related process. So you can, the answer is option D, because you are trying to understand and manage the water-related problems using a hydrological process. Then the next question is, an empirical model is also called as. If you remember, I've told that empirical model is also called as black box model because we don't know. We use different kind of models like data driven or statistical models, but without any physical significance. So it's a black box model. We don't have complete idea of how it is performing, why the model is performing well, etc., or why it is not performing well. So that's why it's called as black box model. So the next question is, the model based on fundamental physics and process governing equations is called as. Option A, empirical. Option B, conceptual. Option C, process based. Option D, deterministic. We know in case of empirical models, there is no physical significance and we don't have any process governing equations. In case of conceptual, some are explained by physics and process based, but some are we some equations are just developed without any physical meaning. But in case of process based models, all the equations or the entire model is set up based on fundamental physics and also process governing equations. So now let's look into the parts like what is model calibration, validation, performance checks, etc. within a basic, within a hydrological model. So the next topic is model model calibration. So it's a process of estimating model parameters. Okay. So model predictions are compared with observed data, and then we will measure some performance metrics. Using that, we'll try to identify the parameters of the model. So it is a process of estimating model parameters. And in this case, The model parameters are of two types. One is physical parameters, another one is process parameters. So physical parameter represents the physical properties of the catchment, like example, the catchment slope, porosity, hydraulic conductivity, etc. But in case of process parameters, it will represent the catchment characteristics which are non-measurable generally. For example, Manning's roughness will be a catchment characteristic parameter. Then we have model validation, which is a crucial step in assessing the accuracy and reliability of crucial step in assessing the accuracy and reliability of hydrological model. So then we will see into what is calibration and validation. Main difference. In both of these steps, what we try to do is we'll compare the modeled data with respect to observed data. But in case of calibration, we will try to use different multiple parameters and we will apply these multiple parameters and generate the model results. Okay. But in case of validation, one single parameter set will be used, which won't be varied across the different observations that we are using. So also the input data sets that going into calibration and validation sets are different. Okay. So model parameters can be changed in calibration process. The input data sets are different for calibration and validation sets. So what are the data requirements and test procedures? We will see now. So the data required. So generally what we will do is suppose we have like the data from 1980 to 2020. That means like we have 40 years of data, right? So around the 70%, we will use 70% of the data we will use for calibration and 30% of it will be used for validation. So in the case of calibration, what we will do is we will do, suppose if we are doing it manually, we will take different set of parameters, huh? And then we will try to simulate the stream flow and we will try to see which set of parameters is giving us the minimum error. That is our best parameter set, optimized parameter set. And that optimized parameter set that we got in calibration set is used in validation data, and we'll simulate the stream flow. And we will compare with the observed data as well, and we'll see how the error is there. So this is how the calibration and validation is working out. So what exactly is the difference is that in the case of validation step, the parameters that we have obtained is only based on this 70% of data. So the parameters don't have any idea about the data sets that are involved in this validation set. So that's how we will know whether the parameters that we got in calibration set are overfitting the data or not based on validation because it doesn't know the data. So if it is able to simulate perform well in this validation set as well, then the parameters are not overfitting and they are a very good parameter set. So if it is performing well in calibration and not in validation set, then it means that the parameters has overfitted the data. Then we have different procedures like how we the split sample test. So in case of split sample test, what we will do is one period of observations is used for model calibration, and one or more separate periods for model validation. As I've told, like suppose we have data from 1980 to 2020. What we will do is from 1980 to 2010 data we are using for setting up the model like calibration purpose, and we'll get the parameters. From 2010 to 2020 we are using the data for validation, or that is one period. If we are looking into more separate period, then what we will do is we have 2010 to 2015 will validate once, and again from 2015 to 2020 data we will use for second validation. Then we have differential split sample test, in which what we will do is suppose we are calibrating the model for low flows, then we will validate for high flows, vice versa. So suppose we are setting up the model for monsoon season and we are validating it for non-monsoon season. So this type of calibration and validation is called as differential split sample technique. Also, it is also called as cross validation. Then we have proxy catchment test, in which we will use data of one catchment for calibration and validate at another catchment. This is mainly used in case of ungauged stations. Suppose what we will do is we consider a station which we will have a observed data, but still we consider it is ungauged. We don't have an observed data, and we'll set up the model and using a station. Suppose this is the catchment. This we have two stations. This is gauged, and this one we consider it as ungauged. So first we'll set up the hydrological model based on the data that is available at this location. And then we will try to simulate the stream flow at this location, and we will see whether it is able to predict stream flow at this location or not using the data. So this kind of approach is called as proxy catchment technique. And then I have discussed like in calibration and validation, we'll try to compare the simulated results with the observed results. So how we will do is that step is called as model evaluation. Okay. In that first step is we have some graphical techniques. As you can see here, first one is time series plot, and these dotted ones are the observed ones, and this line is the estimated one. So initially the model and observed data is almost similar, but it is not able to capture the peak well. So if you see here at this point, there is some time gap. The peak is coming modeled before than the observed peak, and also the amount of peak also is little bit less. Also, this part the model is not able to perform well, and at the end when it's coming the and residing part, the model is performing well. So all these inferences we can get from this time series plot. And then we have a scatter plot where we will plot the data between simulated data and observed data is plotted. Observed data in x-axis and simulated data in y-axis. Okay. And generally the we will have a 1:1 line, that is 45 degrees line, 45 degrees line. And if these points, observed and simulated points, are lying right or left to this point, to this line, then it is a good performing data, or it should lie perfect. If it is lying perfectly on the line, then it's the best model, but generally it won't happen. Okay. And we can also check the performance of this model using a cumulative distribution, cumulative frequency distribution. Like suppose this is the observed data PDF, and this is the simulated data PDF. Then we can see that for a, what is the chance of, uh, what is the value that occurs for a 50% probability is, in observed case it is like around 23 degrees, and in the case of simulated it is 32 around. So that means the simulated model, the model is overestimating the temperature, right? So these kind of inferences we can make from the graphs, and we can evaluate if the model is performing well or not. If the CDFs are almost same, then the model is performing well. Also, we can have some quantitative statistics. Like first one is based on standard regression. So as you know, standard regression, suppose if it is a linear, then you will have y-intercept and slope also. Okay. So the relative relationship between observed and simulated ones we will get from this. And the presence of lag and weave is given by the slope and y-intercept. So if slope is equal to 1, slope equal to 1 and intercept is equal to 0, then it's a perfect model. And also then we have another method called Pearson's correlation coefficient, in which it will evaluate the degree of linear relationship. And if it is equal to 1, then 0, then there is no linear relationship. If it is equal to plus or minus 1, perfect relationship it has. Okay. And it is very sensitive to outliers. Then we have coefficient of determination, R square. So it is trying to proportion the variation in measured data that is explained by the model. So if the R square generally varies from 0 to 1, and if it is greater than 0.5, then it is a acceptable model. That means less variance. Okay. And then like standard regression, we have a dimensionless less techniques. In that first one is index of agreement. T is equal to 1 minus sigma of I equal to 1 to n. OI is the observed data set, PI is the predicted data set, whole square. And we have n number of observations. That's why I is varying from 1 to n. sigma of I equal to 1 to n mod pi minus o bar plus mod oi minus o bar whole square. So o bar is the mean of the observed data. OI is the observed data at time step I, and PI is the observed data at predicted predicted data at time step I. So generally this also varies from 0 to 1, and if it is 1, then it is a perfect model and it is sensitive to extremes. The next one is Nash-Sutcliffe efficiency, NSE. NSE equal to 1 minus sigma of I equal to 1 to n observed minus predicted whole square by of I equal to 1 to n observed minus observed mean whole square. Then only this value will vary from minus infinity to 1. And if it is less than 0, then observed mean is a better predicted than the model. Also, even this is also sensitive for peaks. In case of it does overestimation of model performance during peak flows and underestimation during low flows. Then another type of quantification statistic is error index. In this, we have different methods like mean absolute error, mean square error, MAE, MSC, and root mean square error. So in all these cases, if the value is the error value is 0, then it is an ideal value. So the model is perfect. But what we generally do is in practical purpose, RMSE and MAE are mostly used. And these values, if they are less than half of standard deviation of the observed data, then it is a good model. Okay. Next, we have a p-bias error index, which is represented by I equal to observed data minus predicted into 100 by sigma of sum of observed data. So it measures the tendency of simulated data to be larger or smaller than their observed data. Okay. So if the value is positive, then it is model is underestimating bias. If it is negative, it is overestimating the bias. Then in the case of calibration processes, we have discussed there are two types, manual and automation. Okay. Manual and automation. In case of manual, it is trial and error. So it will, as I told, we'll take multiple set of parameters and we will try to simulate stream flow and we'll check which set of parameters is giving us the minimum error. That is our best parameter set. So it will take a lot of time and also it is difficult to create these sets and we might miss out the actual correct parameter set. Also, this will vary based on the person who is doing it, right? Different modelers will assume different parameter sets. So the result will be also different. And also in the case, there is one case called as equifinity in which multiple parameters sets provide equally good and acceptable model parameters, model outputs. So if we have multiple set of parameters which gives us same kind of performance, okay, then this case is called as equifinality. And In case of calibration process, we have discussed about manual, and we also have automatic method where we will have a objective function like suppose minimize root mean square error. So that is a objective function. And to minimize that, we will have an optimization algorithm which will get as the parameters which can minimize this root mean square error. And then we will termination criteria. So we have to repeat this for like 100 times or this kind of criterias we can keep, or we will keep an criteria like RMSE should be less than 0.1. That is also a termination criteria. Okay, these are the steps involved in case of automatic calibration process, which is easier and it is done mostly using computers, okay, not manually. Then we have a topic called sensitivity analysis, in which we are trying to look into how outputs are getting affected due to changes in inputs and model parameters. These are helpful in identifying the key parameters and their required precision. Also, they are helpful in identifying inputs that are contributing most to output variability. Okay. So in this first we have local sensitivity analysis, where we are trying to identify the parameters that have most significant impact on model results and how sensitive the model is to variation in this parameter. So in this case, one parameter is only changed at a time. Okay. So the steps involved are like first we'll identify the model parameters and then we will define an objective function using these parameters and select some parameter values. Like suppose we have a parameter called porosity. What is the range the porosity value porosity can change? So, suppose the porosity value should lie within 0.5 to 1, then we will set like those like the range the parameter can take. Then we will try to put up these parameters and we will run the model using these values and we'll calculate the sensitivity indices. We will discuss about the sensitivity indices next, and then we will try to interpret the results. So, whichever parameter is giving most high sensitivity index, then it means that it is affecting the output more. So, like that, we will draw some conclusion. So, sensitivity indices which are used mostly used are first one is absolute sensitivity coefficient. Yes, that is given by dou observed by dou predicted. So we are considering a partial differentiation here. So the numerical approximation for this will be O2 minus O1 by P2 minus P1. Now this is approximately equal to O of P minus delta P by 2 delta P. Okay. And then in this case, what will happen is the quotient will be dependent on the units of input and output. Suppose input is rainfall, and output is stream flow. It's in meter cube per second. Then the sensitivity quotient will be in this units and which we cannot compare across different models. Okay. So that's why we'll go with relative sensitivity quotient This is equal to dou O by dou P into P by O, predicted by observed. Okay, in this case, the units will be it will be a dimensionless quantity, so we can compare across the models also. Then we have global sensitivity analysis, in which it considers the interaction among model parameters and the joint impact on model outputs. Like we will variance based, it's a variance based approach, and large number of simulations are carried out, and then mean and standard deviation of the output is taken. So let's look into a few of the questions related to this topic. The process of estimating the model parameters is called A. Option A, modeling. Option B, calibration. Option C, validation. Option D, optimization. So remember, in calibration, we are trying to find the model parameters using the calibration dataset. And next question is, what is the primary purpose of model calibration? Option A, to validate model results with observed data. Option B, to adjust model parameters for better accuracy. Option C, to test the model under different scenarios. Option D, to eliminate uncertainties in model hydrological processing. So what we are doing is, like, we are trying to adjust the model parameters for better accuracy. If you remember, in manual case we have talked like told that if we have multiple parameter sets, we will try to identify the parameter set which is giving better accuracy. So we are changing these parameters in the calibration set and we are generating the output. Okay, so that's what we are doing. So it's option B. So next one is, which of the following can be a model parameter? Option A, catchment area. Option B, Mannix roughness coefficient. Option C, porosity. Option D, all of the above. The answer is option B, all of the above. The next question in proxy catchment test involves option A, calibrating the model against data for one catchment and then running a validation set for the other catchment. Option B, calibrate for high flows and validate low flows. Option C, one period of uh, observation is used in model calibration, and one or more separate periods are used in model validation. Option D, only validation of datasets. If you remember, in case of split sample test, the option C is done. Like one period of observation is used for calibration and one or more is used for validation. And in case of uh, differential split sample test, what we will do is we will calibrate the model for high flows and validate for low flows, like that. But in case of a proxy catchment test, we are calibrating the model at one location, okay, one catchment using the data in one catchment, and we are validating it using the data in another catchment. So option is option B. The next question is model test procedures. Is or are? Option A, split sample test. Option B, differential split sample test. Option C, proxy catchment test. Option D, none of the above. Remember, we have discussed all these three. So it is option D. That's correct. The next one is model validation is performed to option E. Ensure that the model works well for a different data set. Option B, adjust the model parameter. Option C, remove bias from the model. Option D, optimize the computational efficiency. So any guesses? So yes, the correct answer is option A. In this, what we are doing is we already have the parameters from the calibration, and using those parameters, we are trying to check how the model is performing for a different data set in validation. So that's why it is option A. So the next question is, expand the term NSC. Option A is Nash-Sutcliffe efficiency. Sorry, Nash sufficient efficiency. Option B, Nash Sutcliffe efficiency. Option C is Nash Sutcliffe effectiveness. Option D, Nash sufficient effectiveness. Yes, the answer is option B. So the next one is when multiple parameter sets provide equally good or acceptable model outputs, it is called as option A equifinality, option B optimization, option C evolution, option C convergence. Any guesses? Yes, the answer is option A, equifinality. So suppose we have like multiple parameter sets which are giving good NSE or root mean square error, same values they are giving, then all parameter sets are applicable. But what we will try to do is whether we will check whether those values are practically possible or not. Okay, in reality. Based on that, we will select the parameter set. So this condition of multiple parameter set providing equally good or acceptable model outputs is called as equifinality. So the next question is in hydrological modeling, parameters with high sensitivity option E have little effect on the outputs. Option B is significantly impact model prediction. Option C are not considered in calibration. Option D is are always assigned fixed values. So if you remember, if yes, the correct answer is option B. The parameters are highly sensitive, it will affect the outputs heavily. So it significantly impact model predictions. So then the next question is relative sensitivity quotient can be expressed as option A dou O by dou P, option B dou O by dou P into P by O, option C dou P by dou O into P, option D is dou P by dou O. So here P is prediction and O is observed data, and the answer is the correct answer is option B. Dou by dou P into P by O. Okay. The next question is the complexity of the model escalates from small option A smaller to longer time scale, option B process based to empirical relationship, option C is larger to smaller spatial scale, option D
Next page.
sorry, okay, is it visible now? Yeah. So the next question is complexity of the model escalates from option A smaller to longer time scale, option B process based to empirical relationships, option C larger to smaller spatial scale, option D none of the above. So the answer is option C as it is visible on the screen. If you are going to smaller time spatial scale, that is like suppose you are developing a model, suppose you are developing a lump model for entire basin, you have a one single model, then it is a very simple model. Okay, but if for the similar same watershed, you are trying to develop the distributed model, that is like you are considering grids within the model. So you'll take huge data set is required, and to process it and calibrate and validate these kind of models, it will be very complex. So when you go for smaller spatial scale like this one, then it will be, the complexity of the model increases. So now let's look into the hydrological machine learning in hydrology. So nowadays it's very popular, the terms like AI, ML. Okay. So what exactly is AI? Artificial intelligence. It is the intelligence expressed by machines rather than humans or animals. Suppose if you take examples like Alexa, so it can, if you ask anything, it will give you reply. So it is developed by the, so it is a machine learned model. So it is not, it doesn't work like the human beings. And next, in that we are talking about machine learning, which is a subpart of artificial intelligence. Okay. And in that we are trying, it will enable the computers to automatically improve performance through experience and use of data. Okay. So suppose if you have a data set, then you are trying to see how the, 1 second, let me connect charger. Yeah. Sorry for the disturbance. And now we are talking about machine learning. Machine learning is a subset of AI, and it's a learning algorithm that will enable the computers to automatically improve the performance through experience and use of data. So suppose we have a data sets, like you have images of apple or bananas, like that, and we are setting up, we are using machine learning model to classify this images into apple and banana. So using the properties like the apple is red in color, banana is long and elongated, and it's yellow in color. Based on these characteristics, it will develop a model. Okay. And using that, it will try to improve the results. Then we have deep learning, which is also a subset of machine learning that is used for inspired by the functionality of the brains. It's called the neurons. So which lead to concept of artificial neural networks, allowing them to process vast amount of data and identify complex matters. So main difference between these two machine learning and deep learning techniques are, so from the data sets we have to extract some features, and using these features, then only it can do classification or regression problem. But in case of deep learning, from the data itself, data plus feature extraction is done by deep learning model itself. And then they classify. Using the raw data itself, classification is occurring. Okay. And we have different types of machine learning models, like supervised models, in which both input and output data sets are provided, and based on the input and output, the model is set up. So supervised is nothing but it knows the output data. In case of the other one is unsupervised machine learning model, in which only output is there, and based on the characteristics of the input, sorry, only input data is there, no output data is given. So based on the characteristics of the input data, what it will try to do is it will only segregate the data into multiple classes. Suppose I have given example, like we have apple and banana, and based on the characteristics of an apple and banana will be different. So based on these characteristics that it can extract from the input data set, it will classify the data. It will give the labels apple, banana, grapes, like that. Okay. So, and once it gives the results, and based on the output, it will only try to improve it will be like an iteration process, and it will try to improve the results. Next, we have reinforcement ML, in which, in this also, we don't have we won't give an output data set, but the input data set that we are giving it will be an sequential input data with actions taken at each step. Okay. So mostly in case of supervised machine learning model, it can do regression analysis as well as classification. So what is regression means? Suppose in case of if the output is real and variable, then it is a regression variable. Suppose if you are trying to predict stream flow from rainfall and temperature. Stream flow is a continuous variable. It can vary from 0 to infinity. So we are trying to set up a regression model to generate the output which varies from 0 to infinity. But in case of classification, we have specific classes. Like suppose there is a rain or no rain, high flow or low flow. So if the flow value is greater than 50 cumets, then it is a high flow. If it is less than that, it's a low flow. Then what we will do for low flow, we will assign a label called 0, and for high flow, we will assign label 1, like that. So this is called classification. We are trying to just classify the data. Then in case of unsupervised model, based on, I have discussed, based on the input data itself, it will extract some feature and try to find some hidden patterns that are there within the data and try to assign labels to it. It's a very complex and unstructured data, and the example for this is k-means. Then we have reinforced machine learning model, which will operate in dynamic environment and learn from the collected experience. So the next one is machine learning in hydrological processes. First one we will be talking about is ML techniques in hydrology. First is regression method, in which it will establish a relation between the dependent and independent variable based on concept of maximum likelihood estimation. Okay, and the dependent variable is estimated using the independent variable values. Next one is neural networks. So in this we have two types, ANN artificial neural networks and RNN recurrent neural networks. So here ANN is there has artificial neurons, and these neurons are connected in neural network pattern by weights to perform the task. Okay. Generally this neural network will look like, suppose you have an input data and output data, and in input you have multiple variables, and output can be one, multiple outputs, or single variables. We have some hidden layers. Okay, in hidden layers, these hidden layers are performed based on some weights. So we assign some weights for this. So from input to go to this hidden layer, then some weights are assigned, then we'll get an hidden layer, and then some weights are again there here, and using that one more hidden layer is formed, like that. Some this neural network connection is developed based on some weights. Okay, and in case of recurrent neural networks, so the main thing is that in this case, in case of ANN, it is not dependent on the previous time step. In RNN, recurrent neural network, the output is dependent on the previous time step. So where the output from previous step is fed as input to current time step through recurrent connections of hidden steps. This is called as RNN. Okay. And also the next one is decision tree, which is mainly useful for classification and regression. It has like a flow. It is a flow chart type of tree-like structure. Suppose we have rainfall data. We assign some task to it. Rainfall greater than 10 mm. Rainfall less than 10 mm. If it is yes, then if it is a greater than 10 mm, high rainfall event. If it is no, then it is a low rainfall event. So like that, we can classify based on some questions asked to it, and the structure will be like a flow chart and tree structure. Okay, with the leaf nodes. This is called as root node. This is called as leaf node. It is ending here. It cannot branch out more. So it is a leaf node. And in between is called as intermediate nodes or branch nodes, like that we have. So one example for this is random forest method. Next we have support vector regression. Support vector regression. Here if you remember, it will be somewhat similar to linear regression, but what will happen is, if we are working on classification problem, it will try to estimate the best line and also a boundary. Okay. So based on this, if the points are lying outside this boundary, then on this side of boundary, it is classified as 1. If it is lying on this side of boundary, it is classified as 0. So instead of just creating a one best line, it is trying to estimate a boundary. And these errors are classified from this boundary. Okay. And in case of linear regression also, what it will do is, suppose this is our best fit line from linear regression. But in case of support vector regression, again some boundary will occur. And only the points that are lying outside this boundary are the reason for the errors. Okay, all these points which are lying within this boundary are the best fit lines. Means that the model is able to predict these points. So only the points that are lying outside this boundary are giving us the error. Okay, the next we have nearest neighbor method, which is mostly useful for classification. And based on the old data, what we will try to do is we have data like this. This is set A and this is set B. Okay. And if the new data is here, if it is lying to set A or B, based on that, we will assign a label to this. Since we know that we can see that it is closer to set A, so it is labeled as A. So this is how nearest neighbor method will work. And we generally, when we are applying any machine learning models or anything, like we will do some data pre-processing in which we will handle missing data and encoding, decoding. Suppose encoding, decoding means here, if you see in this example, I'm saying if the rainfall value is greater than 10 mm, it's a high flow, high rainfall. If it is less than that, it's a low rainfall. So we cannot just use that, give that as condition. What we will give is we will convert the data into 0 and 1 format like that. Okay, if it is less than 10 mm, we will give as 0 label. If it's greater than 10 mm, 1 label. So that is called as encoding decoding method. So that way it is easy to set up the model, calibrate and validate it also. And then feature scaling also we will do, in which we will try to standardize the data sets so that because if we have multiple variables, suppose rainfall, temperature, stream flow, a temperature for Indian basin will vary from 15 degrees Celsius to 50 degrees Celsius. So the variation is less. But in case of precipitation, it can vary from 0 to 200 or 150 like that. So the variation is more. So this should not affect the model. So that's why what we will try to do is we'll standardize it so that the values will lie, both the values, both the temperature and precipitation values will lie in between 0 and 1 so that the model can be more accurate. So also we have talked about how we will split the data. Similar to the hydrological modeling, in machine learning also we'll split the data into training set, validation, and test set. 70% might be used for training the data and we'll get the model parameters and all. Then 50%, 15% will use it for validating, and also next 15% we also use for testing the data. Most of validation and testing is almost similar methods. Okay. Now let's look into some questions related to the machine learning applications in hydrology. First question is, which one of the following is not the classification of ML? Option E, supervised ML. Option B, reinforcement ML. Option C, unsupervised ML. Option D, simple ML. So remember, we have discussed about all these three. So the answer is yes, option D. Then the next question is, which algorithm is used to create the best line or decision boundary that can segregate n-dimensional space into classes? Option A, k nearest neighbor. Option B, decision tree. Option C, random forest. Option D, support vector. regression machine. So if you remember, we have discussed about a decision boundary and best fit line in support vector machine. So it is used to segregate n-dimensional space into classes. So the answer is support vector machine. Next, the question is the most popular choices for model evaluation are cumulative frequency distribution, R square, NSE, RMSE, and P bias. Option B, time series plot, R square, NSE, RMSE, and P bias. Option C, time series plot of R square, index of agreement, RMSE, and percentage bias. Option D, cumulative frequency distribution, R square, index of agreement, RMSE, and percentage bias. So the answer is option B because it involves all the measures. Like we have talked about error measure, graphical representation. Okay, all these are very important. Okay, when you are trying to evaluate models. So most commonly these are the ones that we use in hydrology purpose for evaluating a model. So that's it for today. If you have any questions, you can ask me. Anything, any questions related to what is model, what are hydrological models, different types of hydrological models, why we are using it, and how we are doing calibration, validation, and how we are evaluating the performance of a model and application of machine learning in hydrology. So if there are no questions, we will end the session. Thank you for watching.